Hi guys, my name is Japheth, and today I'll be talking about the Petra storage engine, which I built as I was learning about storage engines and database stuff. In a previous video, I did a conceptual overview of the parts and how they work. And then today I'm going to do a deep dive and the actual code walkthrough of the internals. At the moment, uh, the components that the storage engine has is the disk management, as like we saw the other day, buffer pool management, index management. It doesn't have transactions and doesn't support recovery yet. So we'll be going through the code base bottom up, like router. And if you have any questions, you can leave them in the comment. And then I'll get to them after I'm done with the presentation. So we're going to start with the storage layer, the storage component. So we'll start with the disk manager, then I'll go to the disk scheduler, and then the other components as we go. So I'm going to start with the disk manager, which is like the simplest part of the whole storage engine in my implementation, because all it does is just writes pages from the initial video. If you've not watched, it might be helpful to go watch it now or after this. But a page is a 4KB size. A page is 4 kilobytes in size. So the disk manager simply reads and writes 4KB slots into a file, which is what we have here. If you look at the disk manager struct, we see that it has access to a file, and that is the file that we read and write to. Right. So this is the simplest bit of the whole storage engine. And like I said, we don't read and write directly to the file. We have a disk scheduler. The biggest benefit of the disk scheduler is that it helps us provide an asynchronous interface to the buffer pool manager. So what that means is a buffer pool manager can submit a disk request to read or write, and then do other things, and then like read the result whenever it's ready, or wait for the result whenever it's ready. So we look at how it does that. First, let's see the disk schedule. Let's look at the disk scheduler struct. We see there is a request channel. This is where we submit disk requests. There is an instance of the disk manager, which gives us the read or write interface. And then we have a page queue. So if you watch the other video, you remember that I said we have a per page queue. So each page, requests for a page go into one queue. Requests for another page go into another queue. This help us take advantage of the internal disk parallelism, where a disk can handle multiple writes at the same time. So instead of bottlenecking on the page, on a single page, we have multiple page disk requests. A disk request itself, a disk request itself contains the page ID, the data, but if it is a write request, and if is it a write or read request. So this is the write property help us know if the request is a write or a read request. And the response channel, this is essentially what enables the asynchronicity, because for each disk request that is sent contains a response channel where we will write back the result to, or the disk response to. And as you can see here, the disk response struct has the success flag, and the data, if it's a read request, to contain data. If it's not a read request, then it will just be nil. Right. So let's look at what happens when we create an instance of a scheduler. We create a channel for getting all the requests, and then we have a page queue. So for each page queue, we have a map which maps from int to a disk request, channel. So the int here will be the page ID. So for each page, we'll have a channel associated with it. and in that channel is where we'll put the request for that particular page. And then we have a lock. We'll see where we're using this, and then we have a page queue lock, and then we have a scheduler lock. And then we start a Go routine to handle disk requests. This Go routine runs indefinitely in the background. So let's look at the schedule method. It's essentially just whatever disk request is given, it puts it in the disk request channel. This is the scheduler channel, like the global scheduler channel. And then now this is the Go routine that runs indefinitely in the background, handle disk request. What it does is it reads from the disk request channel, and then it acquires a page lock. This page queue lock. We want to acquire the lock whenever we want to modify the page queue, and then we check if like a channel already or a queue for that page already exists. If it doesn't, we create one. We're providing some buffering, and then we unlock. But if it already exists, then we simply add the request to that page's queue. And if indeed if we created a new channel, or if we created a new queue for a page, this is a page that we didn't know before, we start a page worker, and we provide the page worker with the page ID for that worker and the channel and the queue for that particular page. Channel and queue are synonymous in my implementation, so that's why I keep on switching between the two. So let's look at the page worker, which runs indefinitely. Well, not indefinitely. Yeah. So we start a loop for select, and then we check if there is any requests in the queue. If there is a request, if it is a write request, then we tell the disk manager to write whatever was provided in the disk request, with the disk request, the data in the disk request, and then we supply a response back to the response channel, which was in the like I said, a disk request contains a response channel. So for that particular request, we write back a response to it. If it is a read request, we just tell the disk manager to read that particular page, and then we return back. We return a response, a success, and that. If it's false, we just say, hey, success was false. And then if there is nothing in the channel, then we want to delete the queue for that particular page to avoid leaks. So that is the disk scheduler. So after this level, the next component is the buffer manager, which has multiple parts to it. So it first has the LRK replacer, which is our page replacement policy, and determines what pages to evict from the buffer pool. And it also contains a frame, which is now a representation of a slot in memory, and then that is what is either read or written to. So I'm going to start with the LRK, the page replacement policy. So first, the LRK replacer is implemented as a doubly linked list. So that's why you see there is a previous and the next node. It contains a frame ID. K should be the number of accesses. Wait, I don't remember what K is, but we'll see what K is. History is the number of accesses in history, and then is evictable, whether it's evictable or not. Oh yes, okay, we just check has it been accessed K times, yes or no. So that's what we use K for. K access gives us the last access so that we know whether to evict this or not. And then add timestamps of which time a node is accessed or a frame is accessed in that case. We keep track of when it was last accessed. Okay. Let me go to the LRUK replacer itself. So when we create an instance of the LRUK replacer, we provide k, which again is the number of accesses. Could be 5 times, could be 2 times, whatever number of the last k accesses that we care about. Mutex, again, this is just for concurrency control, to make sure that we always hold a lock before updating the LRUK replacer. A node store maps from frame ID to an LRUK node, so that we can tell the buffer pool, okay, this is the node, this is the frame that we should evict. Current size, timestamp will be, we're going to monotonously increase it every time we access, every time there is an access. Of course, the head and tail and the capacity of the replacer, the amount of nodes the replacer has. So whenever a frame is accessed, we want to record access for that frame. Like we want to know that, okay, this frame has been accessed. So like I said, we increase the timestamp monotonously. So for every access, timestamp is incremented by 1. And then we get the node for that particular frame. If the node exists, then we add the timestamp, and then we move the node to the front of the queue, because we want the nodes to remove, to evict at the back of the queue. If the node doesn't exist, then we add it. It becomes a new node. So set evictable is called when say the buffer pool is done with a frame and we want to be able to evict it at some point in the future. So we mark that frame as evictable. And then evict is the core of the whole, is the point of the whole replacement policy, whereby it returns the ID of the frame that is to be deleted. So the algorithm is quite straightforward. Essentially, what we want to do is we check which frame is the least recently used, but also infrequently accessed. And then that is the frame that we evict. We tell the buffer manager, we tell the buffer pool manager, this is the frame that you should evict and make available for the next page that is to be read or written. And then we'll remove, again, straightforward as well, is the node that we want to remove from the queue, from the buffer pool manager. And then size, to return the size of the size of the W linked list, and then add node to add a node to the W linked list again. So that should be quite straightforward. Most of the interesting bit is actually in the buffer pool manager, and I'm going to explain a pattern I used, which felt and still feels very unnatural for Go, but more appropriate for C++, but then I'll explain why. And if someone has a better idea, then they can tell me what other approach they could have used. So for the buffer pool manager, let me show you the frame. So a frame has, of course, a lock as well, because we don't want multiple Go routines, for example, to write without a lock, without holding a lock to the frame, because then we'll have a rest condition. So the frame has an ID, the data it holds, pins. So pins, we increment a pin whenever there is, say, a process or a Go routine that is reading from the page or using a frame. So all those all Go routines that use a frame, they attach a pin to it. And once a frame is pinned, that means it cannot be evicted. A frame can only be evicted from the buffer pool manager if all the pins, if the pin count is 0. Dirty, if it's been written to, this is important because for all dirty frames, we need to make sure that they are flushed to disk before we evict, before we make that frame available for another page. and the page ID, that is the pages whose data is in the frame. Right. So this is where we create an instance of the buffer pool manager. So we say the frames, the amount of frames that the buffer pool manager has, and the amount of free frames. So at the beginning, the count of frames and free frames is going to be equal because all frames are free in the beginning. And then, so for each, and then you go through, and then you create now the frame struct for each available slot. We give it an ID, which is like the position of the frame in the buffer pool manager, and the data that it holds. Not that we're not setting the page ID. This is just the frame ID, which is the position of the frame in the buffer pool. And then, so for each frame, for each instance of frames, we put a frame struct, and then free frames just keeps track of the ID or the position, the slot of the frame in the buffer pool. Because we only use free frames to determine, okay, what slot is available, and then we give that out. So we create an instance of the buffer pool manager with a lock, a lock, and then the list of frames and the page table. So a page table maps from page ID to slot to frame ID essentially, but it's page ID to a frame in the buffer pool, which has data for that page. A replacer, we've already seen our page replacement policy. Disk scheduler, like we've seen again, it's what the buffer pool makes request to. The buffer pool makes disk requests submits disk request to the disk scheduler, and then disk scheduler uses the disk manager to either read or write or to process that disk request. Free frames is a list of all available frames to use. So this instance here is a conditional. We'll see how it works, but essentially is sometimes the frames can be full or can be occupied by some, say, all Go routines. Each Go routine or each process is using a frame in memory. So, and another Go routine makes a request to use a frame. So this essentially tells it to wait until a frame becomes available to process that Go routine's request essentially. So what happens when reading a page? Well, first is we acquire a lock for the buffer pool manager because we're going to change this its attributes or its properties. And the first task is to try and get a frame, right? So here we get into is an infinite loop. First we check we check the page table if that frame is already in memory. So if this is true, if a page table contains a page ID to slot to a frame ID mapping, that means that page is already in memory. So what we do is we get it, we read the frame, and then we tell the replacement policy, okay, record access to this frame and set its evictability to false. Like this frame should not be evicted while we are using it. And then we acquire a read lock for that particular frame. So what this means is multiple Gaussians can read the frame to increase or to improve performance rather. But if it was an exclusive lock, then that means only one Gaussian will be able to read a frame. In this case, we want as many as possible to read. But if we're writing, then we only want one routine to write to that frame. And of course, we pin it. Like I said, if a frame's pin is greater than 0, then that frame cannot be evicted. Only when the pin count is 0 and it's evictable, set to evictable, can the frame be evicted. This is the part where I said felt very unnatural for Go. And for those familiar with C++, this is the equivalent of the resource acquisition is initialization pattern. And very, it's also very familiar to how mutex locks work in Rust, whereby the lock actually actually protects the data it holds, right? So the page guard, essentially it guards the page that it holds. So let's see what it does. So this is a new page guard where we return the page guard containing, of course, the frame and an instance of the buffer pool manager. And it has a method called drop. So this is the acquisition is in the initialization bit, whereby when the frame is dropped, or when the guard is dropped, that means you are done with that frame. That means like if a coroutine acquires a page guard, then it holds the guard until it is done with it. But when it is when it
Japheth,
drops
sorry.
it, yes, yep.
Could you please zoom in a little bit? I think
Oh,
people can't see the code really well.
wow. Is that better?
Yes, I believe so.
Right.
Thank you.
All right. So I'm not sure how far back people want me to go. But I guess I just forge ahead, and if there is any questions, I'll be happy to answer. Right. So, like I was saying, this is the pattern I used that felt very unnatural for Go, because that means in the future, whenever I'm done with a frame or a page, I have to drop the guard manually or explicitly. Whereas in C++, I wouldn't have to do the dropping explicitly. So if anyone has a better idea, open to suggestions. So, but this drop now will drop a page, will drop a guard whenever we're done with the page. So in this case here, we first we unpin to reduce the pin count, and then if the pin count is 0, we set that page that frame as evictable. So if the pin guard is 0, that means there is no other process or routine is using that page, then we can set it to evictable. The next time, and if the buffer pool is full, then that page will be a candidate for eviction. And then we release our lock, and then this is the bit where I was talking about the conditional wait. So now we signal, we send a signal, and whoever was waiting on a free page, whichever process that was waiting on a free page can now access that page. It's very similar for both read and write page guards. So it's all very similar. So that's the idea behind the guard. And again, like if anyone has a better idea, please let me know. So this is if the frame is already, or if the page is already buffered, or is already cached in the buffer pool. So what if the frame is not in the frame? So we first check in the free frames. We check, okay, is the size of free frames greater than 0? I mean, is there any free frame? If there is, we get the frame ID, and then we actually get the frame here, and then we reduce the list of available free frames. That's what all this does. What this does, just reduce the list of free frames. Else, if there is no free frames, then we have to tell the evictor to please evict a page, or to tell us what page to evict, and which gives us the ID, which will now be the frame ID. So here we go to the frames, frame map, we get that particular frame, and then we flash it. By flashing it means write it to disk. So before we do anything with that frame that we've just evicted, flash its contents first. Right. So if we got a frame, we remove it from the page map, the page table frame ID map, and then we reset it. We say for that page ID, use this frame, and then we record access. We record as access again, and then we set it evictable to false. So while we are using this frame, it cannot be evicted. We acquire a read lock. Okay, so this here is actually should be a bug, because we should acquire an exclusive lock, because now we're actually updating the frame state. So maybe you can fix, or someone can send up here, we reset the frame content, because now we want to reuse that frame with another page's data. So we pin it to avoid it being evicted while we're using. And then we set the page ID, because this is a new page now reusing a frame. And then this is the point where we submit a disk. First we create a disk request. And then we schedule that disk request. Essentially, we say we create a new disk request. This is a read disk request, because this here should be, yeah, is right false. So this is a read disk request. So we tell the disk scheduler, please give me this page. And then this is where the asynchronicity comes in. Here, between making the request and actually using the response, we can do anything. We can do any number of things. But for my implementation, we just whenever that response is ready, because in Go, reading in a channel will block until there is something to read from. So we get the response, and then we copy data from the response into the frame, and then we finally return a page guide. So, but if we didn't get a frame, if a frame was nil, like if we tried to get a frame and then there was nothing here to evict, so that means the buffer pool is held up. Then this whatever process or routine that I called read, this should be read page, will wait until it is signaled by another process that, okay, you can now go ahead and try again. Some implementation increase the size of the buffer pool as it gets filled up. They increase the size of the buffer pool. Mine doesn't. It's a very similar process for writing a page as well. First, well, we require the lock, of course. We require a lock for the buffer pool manager itself, and then we get a frame. We record access, set it to false, set the pin, and then we set data to true, because now this is a frame that we want to write data into. And of course, if the frame is already in memory, we simply set its dative property to true, and then we return a write page guard. And like I mentioned, a page guard essentially protects the page until someone is done with it. By someone here could be a routine or a process. So until someone is done with it, and then they will have to drop it explicitly. Again, like I said, this is not very idiomatic for Go. So if anyone has a better idea, please let me know in the comments. So we try to get a frame again, see first if there is any free frames available. If there isn't, evict a frame, and then most of it is similar. I just want to highlight this part here. We make a disk request for that particular. We made a disk request for that particular frame, and then we get the frame's response, and then we copy the frame data into that particular frame. So maybe you can look at the flash. So during flashing, we check if the frame is dirty. If the frame is dirty, remember we're actually doing the writing during flashing. If you are keen, you probably notice this is pretty much it's actually similar to what we're doing during read page, and that is because we need to bring things into memory first. Right. So the actual writing happens when we are flashing a page, and that is where we create a write request. We create a write disk request, and then we schedule that request, and then we wait until it is done. So that's the buffer pool manager. I don't know if there is any question. Yeah. So I'm now going to proceed to the index. Well, one thing I would say is after implementing the B plus tree, it's not the best code. Like I'm not proud of what I wrote, but I was glad that it just worked because it was so painful to get it to work. So I didn't really clean it up. I was just happy it was working, and then I moved on from that. But let's see how the B plus tree works. So before I go to the B plus tree itself, there are two kinds of pages. There is a leaf page, and then there is an internal page. So let me go to B plus tree page, internal page. So let me first start with the header. B plus tree header. Yeah, so a header is essentially just like metadata for that particular page. Of course, that's a page ID. It has a parent because essentially it is a tree, like a binary tree, just that the children and the leaf nodes can have any number of a node can have any number of children. So we have the page ID, we have the parent, the next and the previous. So each for the leaf page, for leaf pages, they form a doubly linked list, which enable scanning or range queries, like say from this page, from this value to this value. So we just call dot next. And just the maximum size and the page type, which is now either a leaf or an internal page, and then keys and values. So for internal, let me get to leaf page first. So for the leaf page, the key value pairs in a database, the key will be, say, the actual, it could be something like the a row ID. Well, it could actually be the ID for that particular row. And then the value will be what is more correctly called as the row ID, which is where exactly on disk that value is. Yeah, but for purpose of demonstration, this could be, say, this is just essentially a key value pair. So this is where the key valueness of the key value storage engine comes into play. So this is where the actual key values are stored at the leaf pages. For internal pages, it still has keys, it still has values, but now the values for an internal page is the position is page IDs. The value is page IDs of the leaf page of its children, essentially. It's the page IDs of its child pages. Whereas for the leaf pages, the values are the actual value that we care about. The rest, and then we say the internal page, we give it a page type was internal, and then the leaf page, the page type is leaf page. All right, so let's go into the B plus tree itself. So starting with a new B plus tree that has nothing completely, we first get the header page, which essentially is the root page. So I think the header page in my implementation will be holding metadata for the storage engine, I think. But again, this is the bit that I was saying felt very unidiomatic for Go, because now I have to drop the guard explicitly. And it's very easy to mess up. It's very error prone. So it was very painful to do that. So we get the data from the header page. This essentially just converted from it essentially deserializes from a struct to binary representation. Yeah, so in this case, we're destructuring to a struct, to a Go struct. And then header page, we create a byte slice into the header page. Okay, I'm not sure what I was thinking here, because I seem to just read the header page and then write it back to deserialize it and then serialize it back. Anyway, like I said, I was just glad that this part was working. I didn't really go back and clean it up. Right. So and then we return an instance of the b plus tree with the key value, whatever type of value and key you want to do. This is using Go generic, so whatever key and value that, whatever data type for key and value that you want. The first page ID is page 1. Right, so let's look the process for getting a value. So just go through the process of getting a value, and then I think wrap up the call because I'm saying I'm like 40 minutes into the call. Right, so we first check if the tree is empty, the binary, the b plus tree is empty. If it is, we just say, hey, it's empty. And then we create, for my implementation, I was returning a list of values in case there is duplicate keys. I'll just return a list of all the values that match that key. So we create that, and then we find the leaf page for this particular. We get the ID of the leaf page of this particular tree. Well, we're finding the leaf page of the page containing the key. So you can look at that here. So this is what we do to get the particular page that has the key in it. And remember that a page is 4 kilobytes wide. So this page will have many other keys, but now, and we could have 1,000 pages, but we just want the page with this key in it. So again, we start with the root page ID. We start from the tree root, and then we read that we read that page ID. Again, this is the bit that I was saying it could get is very error prone because you always have to remember to call drop. So if there is an error, we return an error, and then we deserialize that into a struct, into a ghost struct, and then we check if that struct is a leaf page. If you check if that page is a leaf page, if it is, then well and good. We found the page that contains that particular key. If not, we keep on searching. We keep on searching for a page that might contain that particular key. So again, this, like I said, if this is not a leaf page, then that means whatever page you are on is an internal page. So what we do is we need to find the page where that value might be in. But remember that even the children themselves might be internal nodes for internal pages for that particular B plus tree. So we find the page. I'll show the implementation of this method, but then we find that particular page ID that is in the path of the leaf page that contains that key. And then we keep on iterating and looping until we actually find a leaf page that contains that that key. And that's why you see here, we return current page ID is essentially a value. Remember, I said that an internal page has keys and values. So for that particular internal node, we check the value at that particular index, which is what we got here. So that now becomes our new page, which we now have to go all the way back here and then keep iterating again, keep looping. Essentially, this is doing an equivalent of what a binary search of what you will do in a binary search tree to get a particular leaf value. But now here, remember that internal node can have many values, not just 2 children. It can have n children. So that's why we have to loop again for each for that particular page. Loop through all its children, and then we get the particular. We get the next page, which is in the path to the leaf page containing that particular key. I don't know if that is confusing, but if it is confusing, I guess my mission will be accomplished so that there is one more person who doesn't understand B plus trees. Right, so I was in the B plus tree. So where was I? I was in somewhere. I was way up. Yeah, I was getting. Yeah, get. So we've seen how we find a page, a leaf page that contains that key. So if we find the page, we read the page here, and then we deserialize. We deserialize it into a struct, into a ghost struct, so that we can work with it. Again, also this deserialization is rather inefficient. There's a better way of doing it. Could be an alternative to for the serialization is just using a byte slice and then interpret a particular byte slice into a struct, or go from a byte slice to a struct and from a struct to a byte slice. So that would have been a better approach, but I'm just using a library to serialize and deserialize the data. So we get that particular page, and then we get the insert index of that particular page, of that particular key. Sorry. So this is for the values in the leaf page, which are all sorted, by the way. So all the values in the leaf page are sorted, which is the whole point of having a B plus tree. Is this essentially does a binary search to get the particular value, because it gets a key and then returns the index of the value for that corresponds to that particular key. So you get the value index, and then we do some boundary checks, and then we return the value at that particular index. Now, given that key, so the approach is the idea is to, given a key, find the leaf page that contains that key, and then find the index of the value corresponding to that key. Once you found that, then you just simply call the value at method for that particular key. So yeah, all right. I mean, it's not very different for put. It's essentially it's the same approach. You first have to find the leaf page for putting that particular value, and then you might need to move things around to make space for that particular value. But I think one idea that is worth explore, or is worth talking about, is the splitting, is the page split. So yeah, which is here. So yeah, so if we're putting values in a leaf page, and while the size of the leaf page is less than the maximum size of our pages, which we specify, that's fine. But what if the size of the page is greater than the max size? That means we have to split the page, or rather, we have to create a new leaf page to hold the data for that particular, to hold some of the data from the old leaf page. Essentially, if a leaf page, the maximum size of a leaf page is 5 items, and we add a 6th item to that leaf page, then what you want to do is you want to split the leaf page and have 3 values in the old leaf page and the three other values in the new leaf page. So I'll just highlight that here. That this is where we tell the buffer mode, give us a new page ID. We want to write a new page. We get a page guard, and then we create. This is the data for that particular leaf page, new leaf page, and then of course we initialize the leaf page with some information, including the parent, whose parent, because the leaf page that from which we create a new, or the leaf page to which we create a neighbor, they have to share a parent, right? Like it will, for start, it will have the same parent. The new leaf page will have the same parent as the old leaf for start. And then we get the index where we want to insert that particular value, that particular key value pair. And essentially what this is doing here is we're creating a temporary key and value array to hold the key and values for the old leaf page. And then what we do here essentially, I think this is the most important bit, where we now distribute the keys and the values between the old leaf page and the new leaf page. And then from there on, insert parent, which now will we've been dealing with the pages of the leaf so far, but then remember that each leaf page has a parent, right? So this now updates the parents to point correctly to the child. Right. I think that's should give you an idea of how the storage engine works, and I'm happy to stop here and happy to take any questions. So if there is any questions, I'll be happy to take them now. Uh, sure. Shoot or Nkibandi. Um, Overflow pages. Can you explain? Or maybe you can explain what overflow pages are. I'm still learning this stuff, so never mind, Gilbert. Can always catch up later. Oh yeah, so that's what I was explaining. So if a page is already full, because for each leaf page you specify a max size. So if a page is already full, then you create a new leaf page, which will now be starting off can be a neighbor to that particular page. So we create a new leaf page, and then we distribute the data from the old page to the new page, such that say if the maximum size per page was 5, and now we want to add a new value, a new key value pair to a particular page, which means its size is now 6. So we create a new leaf page and then distribute the key value pairs among the two pages. So that's what I was explaining. So if data in a leaf node goes over the page size, then we create a new leaf page and then redistribute the data. Yeah, well, Gilbert, talk is cheap. You do it first. Do it first and then we can talk. All right. Maybe one more minute for questions, and then if there is none, I think we can call it a night. Oh, but Oria said he has 2 questions. He only asked one. What's the second? Oh, I see, I see. Yes, so actually, I'm not supporting variable size key value pairs. Pretty much it's fixed size key value pairs. But if it was variable size, then yeah, we're not supporting that. So yeah, the answer is no, it doesn't support that. But the repo is open source, so please feel free to feel free to make a pull request. At the moment, yes, you have to call sync explicitly, because I was too lazy to have like a background routine that checks for dirty pages and flashes them and writes them to disk. But again, an opportunity for PR if you're interested in that sort of thing. Yeah, and like this was a learning project, so please don't use it in production. But feel free to fork the repo, use and misuse with my blessings. All right, guys, I think I'll call that a night and have a good evening. Yeah, bye.